So welcome everyone. I'm Sebastian, I'm the session chair today, and I also have the pleasure to start with the first presentation. And let me get right to it. So I'm going to present you some early research results of, as I think, pretty interesting case study we are conducting. The topic of the presentation is coping with uncertainty. And what I'm trying to do, I'm trying to convince you that forecasting is not only about being accurate, but in some cases, probably only about being accurate enough. Let me preemptively say that we conducted a qualitative case study. This is what I'm going to present. Since they are usually very rich on data, I have to cut short on some ends, on some theoretical foundations, to make it, still I try to explain everything lean and clear. If there are any questions, feel free to ask afterwards. I'm also available for some video conference afterwards if anybody is interested. Just want to say that in advance. Okay, let's cut right through the chase. Uncertainty is everywhere and we have to deal with it. That's the basic situation more or less every business is facing. Uncertainty is an omnipresent feature in every business environment. Every company must deal with it, and to be successful, a company has to cope with that kind of external dynamics of their environments. However, what we observe is that dealing with uncertainty as an explicit organizational capability seems to reach the consciousness of top management, organizational leaders, particularly over the last decades. Maybe driven by the financial crisis, but I don't want to hypothesize too much here. And this is some development that we in general also observe from, let's say, my home discipline, management, accounting, and control, which is maybe a little bit more unusual for this conference here. But that's also something we observe, particularly from our discipline. And I will tell you a little bit about how this manifests in organizational life. So if we look into some industry surveys, we see that there's a vast amount of resources invested in processes around planning, budgeting, and forecasting. We also see a strong development towards the application of more rolling forecasts in businesses. More dynamic budgeting practices are applied, and financial forecasts are also more integrated into general planning, for example, in S&OP process. So hence also from our management accounting perspective, there's an interest in better understanding how these forecasting processes are working, since they are, let's say, the first element of all the decisions that come afterwards, which we are already familiar with in our discipline, where we already pay a lot of focus to, like budgeting and other planning decisions. So therefore, that's also interesting for us. That's more or less our motivation to have a look at this. If we now want to know what makes a good forecast, what we usually find is forecast error metrics. So that's the go-to KPI to evaluate if a forecast is working fine or not. And there seems to be some common alignment between practitioners and academics. Forecast accuracy is definitely of major concern and is most of the time the focus of studies. I don't want to say that this focus has no reason, or that there's that this is somehow wrong, or that there's no reason for this focus to exist. But I rather want to make the claim that there are indications that in certain circumstances it makes sense to take a wider perspective on forecasting practices, and that this might generate some new insights and can be very beneficial in certain circumstances. So if we look into literature, I'm not the only one who is saying that. There are some other voices that make that claim. For example, we can find a claim that how forecasts are actually produced in practice is not very well understood, or at least is not very comprehensively investigated. That when we look into forecasting processes in particular disciplines, for example, supply chain forecasting, that there are issues surrounding these kind of forecasting practices that go beyond only methodical topics. And also we find studies that indicate that despite low demand forecast accuracy, firms can still attain a high operational performance. And this is what it's about in the end. We want to achieve a high operational performance. And apparently not always forecast accuracy is a driver for that. So how can we contribute with our study? We follow an omnipresent call for more empirical case study research. So we thought we'd give it a try and investigate a demand planning routine in a large semiconductor manufacturer, particularly the demand side of the S&OP process. Characteristic for our case is high external uncertainty, complexity in terms of the product structure, but also internal processes when it comes to the planning process, and a very mature advanced planning system. Then, and that is probably even more interesting, is that in our case company, we don't find any measures for forecast accuracy. So they have demand forecasts, they have different types of information that feed into that, but there is no forecasting accuracy measured. It's basically completely neglected. And that's why we thought that might be interesting to look at. Why is this the case? So what we are doing, we are applying a distributed cognition perspective by Hutchins. That's our theoretical foundation. I don't go into details here, that would lead too far, but I thought you should at least know. And we use this perspective to map out this demand planning routine as a process map, basically, in the end. And based on that process, we then contemplate how this demand planning routine actually is managed and what the role of the demand forecast within this setting is. And let me give you a brief outlook to our findings. So the central role of the demand forecast is not only to reduce uncertainty, but we need to reflect on it as one component for uncertainty management. And here, just a quick overview of the data we collected. We did some research on the spot interviews. We did a small survey. I come back to some of that later. That's the theoretical foundation. Like I said, I don't go into details. I think what's important here is that we look at both humans and technological or external artifacts. So the technology environment of our demand planner, as we introduce him later. And what's exciting about this kind of framework is that we follow the information propagation through the system. So we particularly look at how demand information enter our system, how they are transformed in the system, and then how they are used. In order to apply that perspective, we had to formalize some parts of it. So we introduced something like sensors, where the data are recorded at the system boundaries. We have buffer where information are withheld until a certain criteria is fulfilled. And we have filters where information are reduced. I will not go into details about these formalizations, but you should know them and to understand the process I show afterwards. So this is the result of our process mapping, a little bit simplified. It took a while to get it like this, but this is basically the version of it. And what we see here is we have the demand planner in the center. So this is a person of interest, so to say, because he is the one who is generating demand forecast. And we have two sources he uses to generate a demand forecast. On the one side, let me just real quick use the laser pointer. I hope you all see it. On the one side, we have a customer forecast, which enters our system through an EDI system, and then goes into our PLUI, our planning user interface. So here we have the forecast of individual customers on a very fine granular level, actually. And then we have a marketing forecast coming in here, which is generated by the marketing planner. Why do we have those both? So we are in the semiconductor industry, so we usually have quite long lead times. And even though we have a very nicely coupled supply chain and the customers are actually used to plan ahead of time and enter their forecast to make sure that they really get the products they want, we can see that this pattern, or that these customer forecasts here, the blue bars, only are reliable for the first couple of weeks. And then we can already see, the customer is not so keen on being fully true about this here. Therefore, we also have a marketing forecast, which is generated by another department who looks for the long-term demand information. And those two information are then aggregated on a product level and then used by the demand planner for his demand forecast. And how does he use it? It's actually quite simple. We were a little bit surprised about this as well. The demand planner just takes for the first 13 weeks the average of the customer forecast. He just takes the average, and for the remaining 13 weeks, the average of the marketing forecast, and enters those information as the demand forecast into another interface of the PLUI. And these information are then go further to the advanced planning system. So that's a little bit surprising, because we see here the information they seem to work quite well. So why this averaging? Why reducing information content here even further for going into the APS where the demand supply match in the end happens? And for this, we have to look at the basic functioning of this advanced planning system, because this is already built to handle a certain degree of variance. So we see here what we entered as demand forecast is basically a reservation of capacities. And whenever orders are placed in the system, we have these access orders that are mapped to free capacities of our demand forecast. So we have cases where something might be, let's call it pre-manufactured, but if nothing else is free, like in this case, this excess demand would be accepted with a little bit of lateness, at least in this matching scenario here. And to be able to do that, we have to define a certain range in which this matching is allowed. Obviously, we cannot pre-manufacture something 1 month ahead. That would not work, but for a couple of weeks at least. And this is also a setting the demand planner can set himself. So the APS handles a certain amount of variance already. That is why we don't need this fine, granular, accurate data from the beginning. Obviously, there are exceptions to that. So what we just saw is, let's say, the standard procedure, which works according to our interviews in roughly 70 to 80% of the times of the cases. But in these other situations, there are plenty of reasons that they have to deviate from the simple rule. I will just mention one, for example, high peaks. If we find here in the customer forecast, a very high peak or a very high order is placed here, then this could not be mapped to free capacities if it's too high and the range is too low, if we don't have enough free demand forecast capacities, as I showed earlier here. So this would just get lost. But the demand planner knows that, he knows of this kind of exceptions, and accordingly adjusts his entry here. So he's aware of the system constraints. Knowing that, what is the management philosophy behind that process? What we have here is a process that is specifically designed for exception handling. So these exceptions are somehow stored in the social structures and in the APS. That means whenever there is an exception, the demand planner is aware of it through his experience. This experience might be shared with his team members. So we have some certain cultural control here, some informal information by which this planner knows, okay, in these cases, I need to handle that as an exception. It deviates from my standard. And this is supported by different control mechanisms and communication mechanisms. I don't present deeper now, but they are underlying that. So this tells us that this demand planner has a very high degree of local autonomy and local control. He can basically individually decide when is there an exception, when do I have to protect, and this standard process and this variance handling of the APS. And this is something we also find in our survey. We asked the demand planners in this company how they perceive the performance, and we see that perceived control of their process and decision autonomy are strong driver for perceived performance. And quite counterintuitively, the quality of information they receive barely has an impact. But it makes sense if we look into the literature again, where we see that decision autonomy and local control are indicators for an organic organizational design and uncertainty management. So what that means is we have a very organic process that is able to deal with these uncertainties internally. So our processes adjust to this uncertainty, and we don't have to reduce this uncertainty before the information enter our system boundaries. That is what is meant by that in a nutshell. So to wrap this up as some general preliminary results, because we still have to dig deeper into our data, but that's the general story so far, instead of uncertainty reduction, we find uncertainty management. And uncertainty is addressed ex post within our system and handled at different points. For example, by filtering for this disruption, by a certain amount of variance handling within the APS. And all this is facilitated by an organic organizational design paired with organizational control mechanisms and social structures underlying that. So what that means for our demand forecast is that the demand forecast's role actually is a stable point of orientation that we can decide when these exceptions are necessary and how these exceptions have to be made, rather than having the demand forecast with the goal of uncertainty reduction. And I think this is a quite interesting view on that, and probably also valuable in other contexts. So to close this presentation, I want to say that I'm aware that it's not quite clear what an improvement of forecast accuracy would lead to in our case, but given this design of this process, we can at least expect that the effects are quite small on process performance. And given the time, I skipped my implications. I hope you got the implications from the rest that I just presented. Thank you for your attention. I hope we have like 1 minute left for some questions. Otherwise, I'm also free for some discussion afterwards. Thank you very much. Okay, given that I'm the session chair, are there any questions? According to my time, according to my clock, we still have 3 minutes. So I would be happy also for some critical comments on what I just presented. Do we have anything in the chat? Maybe. No, we don't have anything in the chat. Any other comments?
Sebastian?
Yes.
Okay. Well, can you elaborate? Maybe I've missed it, but can you elaborate again on the point that you made that the demand forecast can be seen as a stable point of orientation?
Mm-hmm.
It was on your conclusion slides.
Mm-hmm. Yeah. So, okay. I go back to this slide, maybe to explain it a little bit more. Since this is our standard procedure to enter the demand forecast into the system, a demand planner becomes aware that he has to change something when that pattern doesn't fit anymore. So when we are confronted with, let's say, a new exception, a new disruption that we don't know about, we would still follow probably that pattern, enter it into the system, but then what the APS gives out is basically the production plan. And in the production plan, we can also follow on lateness and delivery performances. And if we see that our plan leads to a lot of lateness or a bad delivery performance, then we know that something in our forecast is not working properly. And therefore, we can go back and see what is the issue here. So this is why if we have the stable point of orientation, we always know based on here, we have to make some adjustments. Does that make it a little clearer?
Yes, thank you.
Yeah, thanks for the question. It's a little bit difficult, of course, because there are so many other processes related to that, but I hope I could make the point a little bit clearer now. Okay, thanks for the question. In case somebody comes up with any other comments, feel free to contact me. I'm happy about any feedback on that, since we are also not from the forecasting community, at least not in our core research. Okay, given the time, I would like to hand over to the next presenter. And let me just have a quick look. I think next in the list is Patricia Ramos. with her presentation. So if you are ready, you can share your slides and yeah, go ahead and start.
Yes.
I will give you a short sign after 17 minutes, just so you know that you have 3 minutes left.
Thank you, Sebastian. Thank you. Everything is well, the screen?
Perfect, yes.
Okay. My name is Patricia Ramos. I am a professor at the Department of Statistics of the Polytechnical Institute of Porto, and also senior researcher in ESCTech. This work is about building a framework for forecasting retail product sales based on supportive vector machines. So basically the motivation for this work is something that is not new for all of us. That's exactly that the situation that retailers depend strongly on accurate forecasts to manage their supply chains and to manage basically their inventory. They usually typically they want weekly, nowadays daily forecasts at SKU level on every stores namely for replenishment. And of course this actually needs an automatic procedure for forecasting those thousands of SKUs that exist on multiple stores. Of course, we can go to a pool of models and basically try to understand what is the model that performs best. But actually, the best way would be to select the most appropriate forecasting model for each series individually. We know already that the two main approaches for that are information criteria values, which of course are not comparable if we want to use them on different classes of models. And we also have cross-validation, which of course is very computationally expensive and cannot be used in an automatic procedure that has to be so oftenly used. Well, recently, meta-learning approaches using machine learning algorithms, combining also time series techniques, actually are being used to select the best model from a pool. And that's the inspiration for this work. Okay, another interesting thing that most of you have already seen possibly is that that there are quite a big similarity between SKUs, the same SKUs on different stores, especially if these stores are located on the same region. We have on the first row we have one SKU, and on the second row another SKU, and these are plotted in the first column for store A and the second column for store B. And of course, the similarity between the time series is quite impressive. Actually, this takes us to the possibility of possibly training a system based on one store and then use that trained system to choose the best model for the other store. So that's actually the idea that came out and put this idea forward. Okay, another interesting thing is that Petropoulos on 2014 said one sentence that probably all of us has in mind, which is horses for courses, which means that probably there are many forecasting methods, but some of them are more tailored to some types of data than others. And these differences actually could be explored in our favor to be used for model selection. Of course, we would have to characterize our time series based on its characteristics, and that could provide some insights about what model should be more suitable. Of course, the difficulty is to build, of course, a set of features that actually reveal those characteristics and enables the identification of that appropriate model for each SKU. Of course, this set of features have to be related with the trend, with the seasonality, linearity, autocorrelation, entropy, spikeness, and so on. So those kind of features. On the other hand, we have supportive vector machines. Okay, these are machine learning algorithms supervised, and they are mostly used for classification problems and regression analysis. Actually their success is associated with the reduced complexity that they usually offer, solving some overfitting problems with great efficiency, especially on the test sets. In this case, the purpose of using supportive vector machines actually is for classification. And on that scope, basically we have to find an optimal separation function, which is called an hyperplan, that actually will separate our data into one or more classes, in two or more classes that basically are associated with the model that should be used. Okay, so this is the scheme for the automated retail forecasting framework that we developed in this work. We have basically two phases here. We have the first phase on blue, which has to be made in advance. And it is a training phase where we train the supportive vector machine classifier. We should have a set of training SKUs that should be split in training and test period. We should fit the pool of models on this training period, forecast using the fitted models, and then calculate the forecast errors and build the best model based on some error measure. In parallel, we have to calculate the features associated with each SKU. Since we usually have a lot of features, some kind of dimensionality reduction should be used to prevent overfitting, and then both the labels and the factors are used as inputs to train the supportive vector machine. As this supportive vector machine is trained, it can be used to forecast SKUs from other stores, and basically this will only need, for that, it is only thing it will be need is to calculate the features associated with this SKU, apply the supportive vector machine classifier that will give us the best model for this SKU, and then just all we have to do is to fit the model and forecast. Of course, that procedure in blue has to be made in advance and not so regularly, but by using a store of large dimensions. And then that phase in green is that phase that has to be used and is used regularly, weekly or daily, and of course by using that, we can actually select the most appropriate forecasting model for each SKU based on its features. Of course, to make this framework go to work, we need to build a pool of models. In this case, we were thinking about fast-moving goods. So these candidate models should take into account the seasonality, marketing activities, and calendar events. And of course, for that to be used, we have to think about multivariate models, and the three that we used in this work were regression with ARIMA, where the forecast package was used to fit the model, then exponential smoothing with external regressors, and this was done using smooth package, and also the regression with shrinkage parameter, the lasso, which was also used with regressors, where the autoregressive terms were decided based on the partial autocorrelation function of the time series, and these were fitted using GLMNet. To benchmark these, we decided to use also univariate models, because not all SKUs are promoted, not all SKUs have strong seasonality. So, and we decided to also to benchmark this with univariate, and actually use the ones that are above ARIMA, exponential smoothing, and loss without regressors. And then we include the T-bots because of the possibility to work with the equal seasonality by using Fourier terms. Actually, that was the way we model also the seasonality on the other ARIMAs. But that was what we did here, the pool of models, and also seasonal naive. Okay. To see how this framework can be actually evaluated in practice, we used experimental data from a Portuguese retailer where 2 stores were selected. These stores have similar dimensions. We choose fast moving goods, which means that we have sales on 100% of the weeks. These SKUs were selected from the 6 main areas, which are the groceries, the beverage, the cleaning products, some perishables, and these are weekly data. So we are using units sold that we logged. So we have two data samples, one from store A, which were used for training, about 1,000 SKUs, and about 700 SKUs from store B that were using for testing. I already told you, and we already saw that some SKUs have an intense promotional activity and some seasonality also, and can also have some seasonality. We decided to include some external predictors, namely the price, the number of promotion days in the week, the last week of the month, because in Portugal, people are paid at the end of the month, and the last week of the month, usually the sales are boosted. And then we also include the most important calendar events of Portugal, that of course include the Christmas, Easter, and so on. This is a plot of the SKUs distribution in the feature space. Of course, to do that, we used 36 features to characterize the time series. These actually were the features that were used by Pablo Man's work on the M4 competition when he used XGBoost. And that's exactly the same feature. So these were plotted here on a 2-dimensional space by using the first 2 principal components. And as you can see, almost more than 80% of the variability is accounted by these two components. But actually, what I want you to see is that the distribution of the SKUs on the range is quite broad, and we have here a very balanced sample where the training SKUs occupy the feature space, and we have the test set just occupying almost the same space. So you have a very good insight here of this might work well. Okay, another interesting thing is that if we calculate the features correlation matrices, actually, I am talking about the training store and test store. We see that the correlation variability is high, which means that our features are being quite diverse in terms of the characteristics that are being captured by them. And also the interesting thing is that there is a strong similarity between these 2 correlation matrices, which shows actually what was our first suspicion, that actually there is an approximate behavior between SKUs from both stores. I have to say that 78% of stores from SKUs from store B are in store A. Okay, now I have to explain how the supportive vector machine was trained. Okay, this is the scheme for the training, okay? And I am going to explain how this was done. Actually, this was done by using a ruling forecasting origin to have more more errors. And actually, we split each SKU in a training and test period, okay? And at each forecasting origin, we feed the models from the pool and we forecast. And then we, based on the 22 forecasts that we have from each model, we calculate the two error measures, average, relative, May and May's, and we select the model which have the lowest value of the error of each one of these. We decided to do a parallel analysis using these two errors. Okay, and then afterwards, we calculate the features for each SKU using the whole historical period, and the principal components were also obtained. Then, by using the labels that were obtained from the ruling and the principal components, we trained our supportive vector machine. Here you can see what is the best model distribution on the training set. So I am talking about this small step here. And this is the distribution by May's, but actually the distribution by the average, by the May's, very similar to this one. And it's a very positive insight here, where you see that we have 10 models on the pool. Yes, I think it's 10. 8, yes, 8.
And 3 minutes left.
Yes, okay, 10. And actually, the distribution is quite interesting. Of course, the multivariate models are the most the most used, but the other univariate models are also used, which gives us the idea that they are also important to be on the pool. Okay, the SVM parameters tuning was done by a 10-fold cross-validation, and the number of principal components for the 4 supportive vector machines that were tested were also determined by 10-fold cross-validation by using the 2 errors that that I already introduced. Then we have to evaluate our supportive vector machine classifier, and we did that using the training, the test store. On the test store, we split our SKUs in training and test period, calculate the feature, use the classifier to give the best model, fit the best model, forecast with the best model, and then calculate the error. This was done for all the ruling forecasting origins, and the errors for of the average, real May and the May's were calculated on these two errors. And then you have here the results, and the results are quite actually are good, because actually all the 4 kernels that we tested for the supportive vector machines, all the 4 gave better performance than the time series models, multivariate and univariate. Actually, polynomial actually was the one that has the best performance. Actually, after, you can see that this is the evaluation of the performance. So when we have here the model, it means that the model was applied in all the steps. And in this case, when you have the supportive vector machine, you can have different models being applied in different steps and in different SKUs. So the supportive vector machines have a superior performance, even compared with the multivariate models, which actually performed best than the univariate. Okay, in the multivariate, we have to give relevance to regression with ARIMA, which was the best one from the multivariates. Okay, and finally, let me just give you an idea of what was the best model distribution for both errors. Now you don't have so much variability in the models, because the performance for the multivariate ones is quite good, and the machine tends to select these three models, these three multivariate models. But even then, you have a quite good distribution. Of course, RIMA actually is the most one used, but even though we have some distribution here. So I can conclude that actually we could develop an efficient and effective retail forecasting framework for completely automated with model selection. Actually, we have to reinforce that the really expensive computational effort is made in advance. So this framework can be used regularly and can be applied to forecast large number of SKUs at a very low computational cost. We can, of course, generalize the use of this framework not only for fast-moving goods, but also for slow-moving goods, and also for other time granularities. The only thing that you have to do is just to adjust the pool of models. This work also shows the insights that we've been seeing on the recent work, is that there is some enhancement when forecasting techniques using machine learning algorithms are combined with time series models. Also an emphasis should be given to the use of the principal components for the dimensional reduction to prevent overfitting, and this actually can be seen also as a way of mitigating the problem of having to decide what is the best feature selection for each SKU. Okay, and I finish. I hope I didn't take too much time. Okay.
All right. Thank you very much.
Okay.
We're a little bit over the time, so I would prefer to directly get to the next presenter. Maybe a discussion comes up in the chat or afterwards. Okay. Thank you very much.
Thank you, Stefan.
Okay. Then next is Ömer Zeybek with this presentation.
Yes. Do you have my presentation on screen?
Yes.
Is there a problem?
No, it's fine.
Okay. Then I'm starting. Good evening. I am Ömer Zeybek from Migros Ticaret R&D department. Especially, I am interested in data science works in Migros Ticaret, which is a largest retail chain in Turkey. Also, I am a PhD candidate in Istanbul Technical University. Today, I will represent our recent study on sales forecasting with high frequency data, especially store level for hourly intraday forecasting issue. I conduct this research with my colleagues Buse Mert and Defne İdil Eksoca. Here's the typical presentation plan for a student presentation, and let me just don't waste time and start from the introduction. Yes, decisions within a company, especially a retail company, may be grouped under two main headings, which one is strategic decisions, which determine the limits of resources themselves, which they generate a need for longer term forecasting. On the other hand, the second one, tactical decisions, which govern day-to-day operations, demand short-term forecast to be produced as a matter of routine. As retail practitioners in analytics side, we are mostly dealing with the second kind of problems. In this research, we aim to propose a intraday hourly sales forecast system for store level, and we try to provide store managers a hourly 16 hours a forecast with 16 hours horizon to see his or her day ahead and plan his sales activities. Maybe I can make our research questions more abstract by saying about pros and cons. Sales forecast effort for different outlets requires forecasters to assess different models for each outlet, because each outlet has its own characteristics characteristics in time series data, and implementing an intraday hourly forecasting procedure increases presence of these store level specific patterns, the presence of store level specific patterns, 2 folds or 3 folds. The research becomes more complicated by hourly forecasting. A forecasting model for this problem should be both efficient to deal with large quantity of models, and the algorithms should be flexible enough to assess unique patterns of each outlet. So in this research, to ensure this outcomes, we propose a forecasting system using both econometric, statistical, and tree-based machine learning nonlinear methods to create forecasts for each store. Statistical and nonlinear forecasts for each stores are estimated and tested to find out which approach provides a better solution. Maybe I can give a little quick literature survey. Foundations of the approach I said in the previous slide comes from ARIMA methodology on econometric statistical side, which most of us, I think, know. The Box and Jerkins Time Series Analysis and Forecasting Control seminal book dated 1970, and also for extensions of this theory, because it's a 50 years old theory, for extensions of this theory and its application on R programming, we used Heidemans and Antopoulos 2019 forecasting and forecasting principles and practice book. On the machine learning side, on random forest side, the foundations of the approach algorithm was given by Huntington in 1995 with random decision forest algorithm proceeding in the International Conference on Document Analysis and Recognition. Also on the application side, while constructing our models, we can give examples of Fattah and others forecasting demand using ARIMA model paper, and Kane and others comprehension of ARIMA and random forest time series models are two very likely papers with our research. Here you see our time series data for 100 selected stores. I only give subset hourly sales for the week of 21st of February 2020, where, as you see, it's similar to a sinus graphic with a high seasonal pattern, but every store has different hourly seasonality. The peaks and mainly peaks are consolidated at 6 p.m. Between 6 p.m. and 8 p.m. but and the dips are consolidated between 9 p.m. Between 9 p.m. and 10 p.m. But every store has own characteristics in the periodicity, as you can see. In our training data, while building our models for both RF and ARIMA model, we use hourly net sales as endogenous variable and its select values. This is we collect from company database. Also, we use exogenous variables indicating hourly seasonality, day level seasonality. Also, the mean is indicating specific days for retail activity, which is hot in Turkey, feast days, and Ramadan is also an important feature in daily grocery sales in a Muslim country. Also, we use dummies for Mother's Day, Lover's Day, St. Valentine's Day. Also, we added notable promotions done by the company because our company conducts very large promotions, especially in the last quarter of the year. Also, we added variables to represent them. As I said before, there are about 2,300 outlets active, scattered through Turkey belongs to Migros, and we use 100 key outlets in our pilot study in this research. This is from 2018 to 2020 were used to train the models, and project data comprises about 1.1 million hours of observations with 65 distinct features for modeling. Maybe it would be interesting to tell about how we sample 100 most representative stores out of 2,358 stores. We needed to limit number of models estimated while we are trying to assess which one is better, the machine learning side or statistical approach is better. And to do that, we need a more flexible and easy data. To do that, we limit the number of models to be estimated, so we limit the number of stores entering the research. Also, we needed to be representative, because if we can find out the most successful approach, then we can be sure to go next level and forecast all other stores. We choose stratified sampling for best representation. We take our stratas from company's own format scheme, and according to these formats, we created stratas. For each stratas, we calculated number of stores needed to contain in the sample with 2019 turnover share of the stratas. Here you can see for small grocery format, we take 12 stores. For hypermarket, big shopping center format, we take 11 stores, and etc. After doing that, we run a K-means algorithm with one cluster, allowing one cluster, and we try to find out the cluster center of each strata. After that, also we have the observations cluster, observations centroids. Looking at the distance to the strata center, we collected the most the stores most have the least distance to strata centers, and create our 100 store word sample. Maybe I can give some introductive knowledge about ARIMA estimation. As I said before, we use Box-Jerkins ARIMA estimation, but this is we use its extended formation ARIMAX with exogenous variables. Also, we use Fable package in R, which uses automatic model selection with procedure proposed in Heidemann and Kandar 2008, which guarantees valid estimation with lowest IQ level. Also, all ARIMA models are estimated over stationary target variables transformed using lambda factor proposed in Box 1964 methodology. Both for RF and econometric estimations, we trained models from 2018 January to 2020 February until the end of the 2020 January, and we use validation as a test period. We use the week of 27th of January 2020. We try to filter COVID effects, because due to curfews taken at these days, mainly hourly sales was very disrupted in Migros sales. Here you see our ARIMA estimations and outputs. Here is the hour level dummies indicating 8 a.m. and day level dummies and endogenous variable. Here you can see the results of the 100 models are which are plotted overrightly, and here you can see the IQ values for the estimations. There are 2 or 4 models which are not very created, not created a large IC value. Also, for 8 stores, we were unable to estimate Aremax models. We algorithm unable to find roots for them. And for these models, we use RF models. But from that point, we only compare the 92 stores with each other in terms of RF or econometric modeling. Maybe I can give a little information on nonlinear ML estimation or RF estimation. You know, random forest algorithm, which is proposed by Tim Campo in 1995, mostly used for classification, but also it can be used for regression. Here we use random forest estimation with an extension, and we use random forest regressor as a time series on a time series data in coordinates with like KNet done in 2014. Random forest algorithm introduced extra randomness when growing trees instead of the searching for best feature that decision regression decision tree is done. That's why higher bias and lower variance and less overfitting is such. Of course, we need to optimize our hyperparameters to injecting right randomness, right kind of randomness to our random forest model. So we did a grid search procedure. We search for max step from 5 to 30 and number of trees from 10 to 150 by search using search metric root mean square error. And finally, you find hyperparameter set as max step with 20, number of trees with 30. Now I can skip the findings and implications slides. Here you see ARIMA forecast for selected 9 stores in these 100 stores for the week of the 27th of January. You can, as you can see, for the weekdays, our forecasting performance is much more accurate, but for the weekends, our forecasting mostly underestimates the 9 selected stores. Also, in some stores, our ARIMA model failed to create very meaningful results like 3572 numbers and the one 3314 numbers. And when we look for random forest estimations for the same week, 27th of Jan, these are hourly forecasts, by the way. You can see that in weekdays also random forest forecast is better compared to weekends, and it is the same stores like 3572 and 3314 that random forest algorithm also fails to create more accurate results. That give us a clue that some stores maybe need a different approach than RF or ARIMA estimations. That will be the upcoming issues in our research. Here you see the comparison between random forest and ARIMA forecast. These are forecasts, they are not realizations. And you can see both again in same stores, RF and ARIMA model, mostly this moves differently. Finally, for the results, maybe I can give accuracy measures, report accuracy measures. Here, mean absolute errors are in the scale of Turkish liras, which is by now equals to 8. One US dollar is equals to 8 Turkish liras. And as you see, about 500, we have. But this is a pooled. The accuracy measures are pooled sums for 100 stores, and we don't hardly forecasts with horizons with 168 hours, which translates to 1 week ahead forecast, and 24 hours, which translates to 1 day ahead forecast. And you see there are no significant difference between both of them. ARIMA and RF, they are very close to each other. But in terms of masse, when we think masse is the measure that measuring the performance based with your model's performance with Naïve model. Also, there are some problems here because they originate from the source which I said before, which behaves disorderly, which are outliers in estimation and error terms. We can say if ARIMA or RF is solely better and could be used for hourly forecasts. For conclusions, it's evident that accuracy forecast does not diminish considerably in 1 week horizon. In addition, we could not find enough evidence suggesting that RF or ARIMA models superior to each other. However, both forecasts are still vulnerable to sudden shocks and undefined periodical patterns. These are the outlier stores I mentioned. Also, further study is needed for more accurate forecasts, mostly on these outlier stores. In addition, even using big data and parallel computing technologies supported by the company, both approaches require approximately 4 hours for training all models. Maybe we can improve computing efficiency in the future. Thank you very much.
All right, thank you very much, Omer. Since we are still tight on the time, 2 minutes behind, I think we can catch up on that. Please again post the questions in the chat. I think there are already some. No, there are none yet. Maybe there are some coming. And I give the word to Misha Lapinski with the next presentation.
Thank you. I hope you can hear me clear.
Yes, we do. And I would also give you a sign after 17 minutes if you want.
Thank you. Yeah, today I will give you a glimpse how forecasting is applied at REWE. So who are we? We are REWE International. We have a couple of retail chains like Billa, Merco, Penny, and Pipa. We operate in Austria and Central Eastern Europe, like Italy, Hungary, but we're not operating in Germany. In Germany, there's also REWE, but we are a subsidiary of REWE Germany. And we have about 16 billion of revenue and 92,000 employees. Yeah, who am I? I'm a data scientist at the data warehouse at REWE, and I'm here for 2 years now. And I'm also a PhD student at the University of Johannes Kepler University Linz. And if you want to get in touch with me and ask questions, the best way is to get via LinkedIn, because this is something which stays stable over time. So where are we involved at REWE and in the at forecasting? I will only refer to projects where the data warehouse is involved in. So there are also other projects where the colleagues in the business work on, but we are only involved in 3 projects. The first one is called Handel International Promotion Planning Enabler. Also HIPPY as a shortcut. Handel is just retail, it's just German translation. And there we are in the maintaining phase. This means that we are already in production. We are forecasting 130,000 stock keeping units. On weekly basis, we retrain our models. We predict 15 weeks ahead. We do so for 3 countries and 4 chains. But what do we forecast? We have aggregated data of all sales for a country and a firm on daily basis. And we forecast sales, revenue, and profits. As this project went quite well, we have started next to the project another project on store level. And currently this in development. We already have rolled out some firms and some stores, but it's still in development. And just to two months ago, we started with the project of warehouse forecasting. And this is just still in the analysis phases. And just that you know, at REWE, we are currently, at the data warehouse, we're currently 4 data scientists, 2 full-time, 2 part-time data scientists. So at Hippie, at the beginning, were 4 data scientists working. Currently, there are like 2 data scientists working, but not full-time. I work, for instance, also in the other 2 projects. And here we have 1 full-time data scientist and our 2 student part-time data scientists helping together. And we forecast, in the store sales forecast, we have a lot of stock keeping units to forecast. How does our infrastructure look like? At REWE, we have 70 R users. And this way we have a production server, a dev server, and also test servers for updates and for testing new packages or new developments. We also have Shiny infrastructure. And for instance, for Hippie, we have an own infrastructure where we have nodes with 224 threads and 1 terabyte of RAM, and where we parallelize and compute our models. So we use R as our language. We code everything in R, and we have our Studio server installed. And each node, we also have solutions where we only have R installed, and our Studio is only for interactive working, and and the machines with R are just computational nodes. We use Git as version control. And we also have CI and CD implemented, Apache Airflow and Jenkins for automatization. But we also use, for instance, crontab at Linux for starting jobs on a weekly or daily basis. We use Confluence, Jira for organizing ourselves. And at REWE, we have an Oracle database behind it. So we have a connection of R to Oracle. But we also cache our data on SSD drives just to save our Oracle space. Which models do we use? Some of them were already mentioned by the colleagues. But mainly we use random forest, simple linear regressions, and also LSU and ElasticNet linear regressions. We could also implement other models, but currently, never change a winning team. If we will have trouble reaching our goals, then we will switch to other models which also perform well in the literature. Currently, we're not using any GPUs, but in future we might. We do machine learning, so we do evaluate each other. We have always a training set and evaluation set. We do it on weekly basis or on we simulate productive runs on 15 weeks ahead forecasts. At the beginning, we had quite often overlaps in evaluation time periods, but it's also gives you some trouble of having overfitting on certain days and having wrong errors. For instance, if Christmas is twice in your data and you predict Christmas were bad in the model, only because of Christmas we have an underperformance. So we try to not overlap our evaluation periods. We use the mean squared error as an evaluation measure and the scaled mean squared error. We do evaluate by time or by stock keeping unit. There are always different aggregation measures. It always depends which question you want to answer. The MAPE we also use, and this is mainly for business communication. It's easier for the business to work with the MAPE, but the best model for us is always the model with the lowest mean squared error and a reasonable MAPE. I have plotted you some evaluations of, for instance, here for 2 models over time, the scaled mean squared error. And also on the bottom here, you see, okay, on this week, this is an aggregation over weeks. You see that, if the model ID increases, you see the data scientist or the colleague was able to improve the scaled mean squared error at that time. And that's just a glimpse of how we evaluate. And how does our process work for evaluation? We always have a model improvement, a simulation pipeline, and a validation pipeline. A model improvement is, first of all, you always need to have a goal before you develop a new model or you want to make something to make a model better. In the model improvement, all data scientists are quite flexible. They just have their goal. They start developing a model. But then if it is robust to them, they will implement it to a simulation pipeline. A simulation pipeline is over a couple of weeks, where you retrain your model on certain on certain sets, and in this stage, every change you make must be documented. So we always know if you go to the left or to the right, or you tried a new feature, then we always know what has happened, which feature was changed, and what result does this resolve. And everything is reproducible. Simulation pipelines can be smaller or bigger. It depends which firm or also which time horizon we want to improve. And then the last step is the validation pipeline. So if with our judgment a model performs well in simulation pipelines, then it will also run in the validation pipeline, and the validation pipeline can go over a couple of years. And there we can evaluate how does the model behaves as it would be a productive model over time, and if it's good enough to be implemented as a productive model. We have production, and we have the honor to set everything into production by ourselves. But this also gives us some responsibilities. So we always have a review process. We document our code, we discuss, and we never put code into production if not at least two data scientists read this code and have discussed this code. And in the last 2 years, or we already have lost a colleague in the last 2 years, and we are losing, Rewe is losing another data scientist. So we do have brain drain, and with our processes, we could always, or it's still a stable and robust solution we have. Therefore, we also have tests and unit and regression tests for updating processes. We do not Dockerize our models. We are in the updating process every 6 months. We have restartable pipelines, and we also save a lot of metadata, because the business always asks, or there can be misunderstandings, or there can be miscommunication. And then if the business asks you, why does the model doesn't predict a promotion, then you need to answer it quickly and easily. And with the right metadata, you can, if you save the data which you use for training, then it can come out that the promotion was not in the data while training or while predicting. Our models and our code is module-based. This makes it easier for us to track and to exchange features. This is just an overview. So if you want to implement a new data cleaning, then you just exchange a function of the data cleaning, and you put a new name of the model. And then you can just use all the other components of the model, of a working model, and it's much easier and faster to implement new models. And then you can evaluate small changes quite fast. Which features do we use? We have calendar feature, promotion informations. At calendar features, holidays and events are very important, and month and quarters. Of course, if you look at calendar weeks or months and promotions, you always need to pay attention of overfitting, and because there can be some correlation of promotions and months and seasons. Promotion information, we use the promotion and types of promotions. We have very different kinds of promotions. We are we're a company which uses a lot of promotions. This makes it very exciting to work with the data. The price of, we also create price of clusters, and for some companies or for some retail stores, it's a retail change, for instance, for Penny. The duration of promotion is very, very important, and if you work with the duration, or also the day of the promotion, is it the first day of the promotion, the second, or the fifth? It's a very, very good regressor. Stock keeping unit information. We also have, for instance, in how many stores do we observe currently today? How much shelf space does this stock keeping unit have? And of course, we use lag and leads, and also COVID informations, such that the COVID period does not bias our estimates. Let's look at some time series and which challenges do we have. So at the beginning, we have also nice time series with nice seasonal patterns. Then we have we have time series, this 3 time series with promotion. We have very price sensitive customers. So if there's promotion, we have a high increase in demand. And also we have different promotions. Here you see daily, 1-day promotions, couple of days promotions, and also promotions which with different price offs. You see we see also stock keeping units, which are almost more often in promotion than not. And here also a outlier promotion, which you could not observe, or long-lasting promotions. These graphs are, I really took everything away from this graph, so you don't know which goods these are. The scales are also free, so eyeballing is not, will help a bit, but not a lot. And I also have cropped it with different times, so this is also not the same period. So yeah, look at the time series independently. We have in-out goods, which are just for certain times, and then they're off. So we have intermittent demand, and they're with very high share of the total sales, especially at discount shops. One good can make a high share of the whole profit or revenue. And we have also seasonal components like peaches or strawberries, which have high sales, and then they get out. And then you also have these cases where somehow some stores still can sell these goods. So you also have to take care of such observations. Then event-driven observations, for instance, Easter bunnies. Easter bunnies are sold just shortly before Easter and after Easter, or Sant Nicolo, this good is not interesting anymore. Or in Austria, there's also Fasching, which is a very crucial event, which you should take and model such days. We also have change of demand or supply. Mostly it's supply driven, not demand driven, the changes. For instance, it's just an outlisting of a product that we had very nice fluctuation, but then we decided, or maybe the same product is in action, but it just has a new model, a new stock keeping unit ID, and then you need to match them. COVID was crucial and important. You can see, for instance, here this demand for these goods is as high as never before. Sometimes in some goods, the COVID days are as high as a promotion day. In Austria, it was the 13th of March, Friday, the 13th of March, where this high peak is. There was Sankt Anton was shut down, and and that's why it was a Friday, and a lot of people bought a lot of goods. But we also have stock keeping units where demand decreased on such days. This is also driven by the strategy of Rewe, where some parts of the store were closed, such that not big crowds were there, just as a prevention mechanism for the customers. We have a lot to do. These are just some short points. We will still continuously improve our models. We also we have already everything on this list we already have implemented, but we can still improve it. So promotion corrections, sometimes it's just wrong. Wrong promotions are in the data. We don't want just to say garbage in, garbage out, but we also want to improve it, and we can still work on it. New listings work, but they can be better. The connection with the business is good, but it's always business insights are very high value for forecasting and for model improvements, and meta models would also improve our results. Just summing up, if you want to do a project in forecasting, I really recommend you to read the literature. They're like Stephen Colassa and also Philip Gillard did a lot of good papers, and also in Foresight, very good articles. So I really recommend reading them because they are state of the art. We always look for data scientists, so you can apply, and maybe you will work with my colleagues in future. Thank you.
Okay, thank you very much, Micha, for the presentation. I think there are quite a few PhD students in that session, so maybe you want to post these names in the chat in case somebody had not the time to note them down, just as a suggestion. Besides that, are there any questions? We have 1 minute left if there's something you want to ask now.
I have one question already set up in the chat. How do you parameterize calendar effects, especially calendar effects which vary over the different years? For example, Christmas, New Year, yeah, Easter, and so on. Yeah.
We do. You mean how do we save it in our data if we have a process, if people plug it in, or how do we model it?
No, how to model it. You have to incorporate these calendar effects, and the position in the week of Christmas and so on are always different. Yeah. And for example, the gaps between Christmas and New Year vary between different years. Yeah. And so my question is directed to how do you parameterize calendar effects? Yeah. If they vary over the years, and if the position varies also over the years. For example, Christmas is not always on Wednesday and so on. Yeah.
Yes. So if you should, at that time we do not work on weekdays. So if Christmas is on Monday, and next time is on Friday or on Saturday, then we need to look at, like, we have automated tests for that. And if it's on Sunday and then we have 0 sales on Sundays, then we correct for that as well. Then we'll work with leads and lags. And for such days which vary over time, it really is crucial not to overfit. Because if you do a Monday effect for Christmas, then this Monday and you never have observed Saturday, then you really need to pay attention. And then we also evaluate, especially Christmas and Easter, and have different models and different approaches to work with it. And
okay, thank you.
Yeah.
Okay, thank you very much. Then with that, I would suggest we go to the next presenter, which is Adelson Spolidoro, but I think we have this one as a recorded presentation. So I think Jente, you can share your screen with that video.
Can you see it?
Yes, we can see it. Maybe start to check if you also have the audio.
Meu nome é Adilson Spolidoro.
Can you hear the audio as well?
Yes, yes, that works. Can you maybe, so the presentation is longer than 20 minutes. Could you maybe stop it at 41 or something? 5:41?
Okay, yes.
Just that we stay roughly in time at least.
Good idea.
Okay, thanks.
Eu vou apresentar aqui resumo do trabalho apresentado para dissertação de tese apresentada à Faculdade de Ciências Aplicadas da Unicamp para obtenção do título de mestre em Engenharia de Produção, orientado pelo professor Aníbal Tavares de Azevedo. O título do nosso trabalho é Influência de fatores externos na projeção de demanda de venda de produto alimentício biscoito moldado de chocolate. Basicamente, nós vamos falar de uma introdução, breve resumo, fundamentos teóricos, metodologia, resultados de discussões e considerações finais. O objetivo é desenvolver um modelo de previsão de volume de venda de produtos alimentícios, considerando alguns fatores que influenciam a demanda. Desenvolvido um modelo em rede neural e regressão linear de previsão de volume de venda correlacionado com variáveis independentes: preço, investimento em mídia, renda e share, participação no mercado. Um processo combinatório das variáveis independentes indicou a escolha com o menor erro percentual médio e um melhor coeficiente de correlação. O modelo em RNA teve uma performance melhor que o modelo em regressão linear. O setor industrial de alimentos no Brasil, segundo a BIA, processa 58% do que é produzido no campo, 37 mil indústrias, 1,6 milhões de empregos diretos, exporta para 180 países, produz 9,6% do PIB, é responsável por 67% do saldo da balança comercial brasileira e gera um superávit de 28,8 bilhões de dólares. O setor de biscoito, por sua vez, fatura 36,7 bilhões de reais, produz 3,33 milhões de toneladas e possui 47 fabricantes. Uma grande disputa de mercado e um mercado consumidor altamente exigente. Basicamente, nosso escopo de trabalho ele visa a cobrir uma parte do que se chama de Supply Chain Planning Matrix, que é uma estrutura hierárquica com visão integrada do planejamento da cadeia de suprimentos e uma relação entre as atividades de curto, médio e longo prazo, conforme Ivanov em seu livro de 2019. Basicamente, temos 3 patamares de planejamento, que é o curto prazo, médio e longo prazo, nas atividades de compra, produção, distribuição de vendas. Nosso trabalho ele se restringe ao planejamento de vendas de médio prazo e o planejamento de vendas de curto prazo. Conforme já preconizado na literatura, os padrões horizontal, sazonal, ciclo e tendência, esses padrões podem muitas vezes vir combinados em uma mesma série, conforme Makaridax, Wheelwright e Hindeman em 2008. Segundo Mentzer e Moon, nós temos os seguintes modelos abertos de série temporais, de Open Model Time Series, ou TMS, que observa a série Box and Jenkins é um exemplo, modelo fixo de série temporal, Fixed Model Time Series em situações de horizonte de tempo curto, suavização exponencial é um exemplo, e análise de regressão e correlação, que estabelece uma relação entre vendas e variáveis exógenas. Técnicas qualitativas subjetivas, quando não há histórico de demanda, novos produtos, por exemplo. Como fundamento teórico, nós seguiremos, segundo Iderman e Athanasopoulos, 2018, a previsão de demanda envolve as seguintes etapas: a definição do problema, a coleta de informações, a análise preliminar dos dados e escolha do modelo. Basicamente, as séries temporais são descritas como o valor da entrada da série temporal, o componente de tendência, o componente sazonal e o componente aleatório. E há ainda a possibilidade de uma abordagem de decomposição de uma forma aditiva ou multiplicativa. E também temos a suavização exponencial pelo método linear de Holtz, usando 2 constantes, suavização alfa e beta, possuindo valores entre 0 e 1. Temos o nível, a tendência e a previsão propriamente dita. Também a suavização exponencial, o método linear de Holten-Winters, incorpora ao modelo de Holten a constante de suavização de 2 maneiras, a multiplicativa e a aditiva, conforme vemos nessas equações. E a regressão múltipla, que há a famosa equação, onde nós temos um y, que é a previsão no período t, o valor da variável independente no período t, o intercepto e o valor do coeficiente da variável independente. Segundo Secato e Belfort, para as empresas de alimentos pesquisadas que usam regressão linear em suas projeções de demanda, a variável tipo de produto é o fator principal para a escolha do modelo. Nós usaremos uma rede neural e aqui nós podemos observar sinteticamente um modelo simples de neurônio apresentado no livro de Heinken, onde há os sinais de input, são sinais de entrada, os pesos das sinapses, o agregador linear, o limiar de ativação, o potencial de ativação, a função de ativação e o sinal de saída. Basicamente, nós temos a função de ativação, ela pode ser caracterizada em dois grupos, as funções parcialmente diferenciáveis e as funções completamente diferenciáveis. A função parcialmente diferenciável, temos a função limiar simétrica e a função rampa simétrica. As funções completamente diferenciáveis são as funções logística, função tangente hiperbólica, função gaussiana e a função linear. Temos, basicamente, 4 famosos diagramas de topologia de redes neurais. Um exemplo de uma entrada única alimentada pela frente, entrada camadas múltiplas alimentada pela frente, onde o MLP Multilayer Perceptron é um exemplo básico. Temos a rede recorrente de Hopfield e temos a rede de malha. Em nosso trabalho, nós procuraremos medir o erro das previsões através do erro médio absoluto, erro médio quadrático, raiz quadrada, e também o erro percentual médio e o erro percentual absoluto. Nas pesquisas que realizamos nas bases, nós encontramos os seguintes artigos publicados sobre Demand Forecasting Retail, Demand Forecasting Retail Food, Demand Forecasting Retail Food in Neural Network. Porém, as palavras juntas, price, media, income, share, nós não encontramos nenhum artigo publicado que versa sobre essas 4 variáveis em conjunto. Basicamente, o nosso problema, ele visa a um estudo onde temos um biscoito moldado de chocolate com uma linha de produção dedicada, uma produção de 3.600 kg por hora, 30 dias no mês, 24 horas, 4 equipes, revezamento interno, evitando interrupções. As vendas são para grandes redes de supermercados, hipermercados, atacadistas e distribuidores independentes. Todas as ações em marketing são feitas pela própria empresa e as pesquisas de mercado monitoram as informações do que é vendido fora da empresa. A equipe de vendas é composta de diretor comercial, gerentes por região e promotores. E seguiremos as etapas do método preconizado por Hiddeman e Athanasopoulos, de 2018, que é a definição do problema, coleta de informações, análise de preliminar dos dados e escolha do modelo. Basicamente, utilizaremos o volume de venda, as informações de investimento de mídia, o preço de venda, a participação de mercado, que é o share, a renda média, que é a renda obtida através do IPEA, e o faturamento mensal. Como os dados de entrada, teremos o volume, o preço, o investimento em mídia, renda, share e participação no mercado. E desenvolveremos um modelo em rede neural e regressão linear e testaremos a combinação de todas essas 4 variáveis. Basicamente, nessa tabela, nós temos uma pequena amostra dos nossos dados originais de julho de 2016 a outubro de 2017, onde temos o volume, o preço, a mídia, investimento, renda e share, que é a participação no mercado. Basicamente, ao longo de janeiro de 2013 a agosto de 2019, nós tivemos esse perfil de demanda, onde nós observamos um ciclo de baixa em janeiro e uma leve tendência de crescimento. Também observamos o volume faturado, que também apresenta picos de baixa nos meses de janeiro. Isso representa a compra através dos supermercados e dos distribuidores. Ao passo que Esse outro gráfico representa o faturado da indústria para o mercado consumidor. Vemos aqui que há um descompasso entre o que o mercado consome e o faturado, portanto, o que nós chamamos de o efeito chicote. Aqui, através de descompasso entre o que o mercado de fato compra e o que de fato é faturado, há um reflexo nos estoques internos da fabricação. E aqui há um efeito conjunto, onde nós podemos observar que o volume comprado pelo cliente na ponta mais externa da cadeia tem um descompasso em relação ao que é faturado para a indústria, gerando o estoque, que é representado pelas barreiras verticais. Isso é bem definido no artigo de Li e Wang de 2004. Aqui nós apresentamos uma dispersão dos nossos dados em relação ao volume, conforme recomenda Heidemann em sua análise exploratória. Nós observamos também que não existe colinearidade nem heteroscedasticidade nesses dados, portanto, podemos prosseguir com nossa análise. Desenvolveremos um modelo em regressão múltipla em rede neural, onde faremos a discrepância, a separação das tendências e irregularidades. O método clássico de decomposição, preconizado por Heidemann e Athanasopoulos, será usado para decompor essas séries. A série de dados originais é apresentada nessa tabela, e a partir dessa série estabeleceremos as linhas de curva de tendência. Usaremos uma linha polinomial e uma linha linear. A linha de tendência polinomial, apresentado nessa tabela, a linha de tendência linear, apresentado nessa tabela. A partir desse momento, faremos uma decomposição clássica, e através dessa decomposição clássica, ao final, nós temos a recomposição da tendência polinomial aditiva multiplicativa, recomposição da tendência linear aditiva multiplicativa, e usaremos uma rede neural cuja variável y é o volume, x1 preço, x2 mídia, x3 renda e x4 o share de mercado, usando uma rede MLP Multilayer Perceptron. Usando o software Python, a biblioteca do Sklearning, utilizaremos uma camada oculta, 16 neurônios na camada oculta, uma camada de saída, e a tangente hiperbólica como função de ativação.
All right, so this was something different. I hope you could follow along a little bit on the slides at least. but we directly continue with our next presenter, which is Isis Santos Costa. Are you here? Okay, I don't. No, yes, I see this person at least being present. Yes, there we go. Okay.
Yes, I'm here. Can you listen?
Yes.
Are you listening? Okay.
Yeah, now
great.
we hear you and we see your slides. So please go ahead.
Oh, no, here. I'm sorry, I'm not seeing the slides. Oh, I can see here separate. Okay, nice. Good morning or good evening, depending on where you are. From here, Brazil, good afternoon. I brought today a study with Hans Levenbach, is my friend for independent research, and we were thinking of a way to automate the forecast model selection in a way that we can integrate it on an ongoing basis, so that it becomes more easy to just let the models run. So the goal is to establish a system that can be embedded in the forecast decision support system. The procedure is in 7 steps. We start with data preparation, then we run ANOVA so that we can assess the level of variance from each component. Then we determine the sources of variability in this time series. We define a % for each of them. And then what we use here as a tool is the seasonal strength and trend strength factors. And from them, we also have the influence of seasonal and trend. And in the end, we combine the seasonal influence and seasonal influence, trend influence in factors, and then we define empirical charts so that we can apply for each line of products. So we use here data from tourism, monthly hotel room demand. So here we can see that the data is very seasonal, just by observing, just from exploratory data analysis, we could get the seasonality is strong. So we apply the factors and the influence to get the automated results. So the first step, we organize the data in rows. We have the months, and in the columns we have the years, so that we can input the data to an ANOVA and measure the variance of between the years and the variance between the months within a year. So those data are available in the book from Hans Levenbach, Change in Chance and Race. So we use the Excel add-in, the tools for analysis, data analysis. And then we get the data like this. So here we have the source of variation, the rows. We have the sum of squares here from variance, and here's the columns. In the other, we have the other arrows, not trend nor seasonality. So from here, we measure the share of contribution from each source. So for this data, there is 8% of seasonality contributing to variance, 12% of trend, and 3% are other factors. So we can also compare the numbers that we get to visualization of data. So here is the same data where we have here the months, so visualized in a seasonal way, and each line is one of the years of the time series. So we can also here see that the data is very strongly seasonal, and there is a clear pattern of repetition here, with more demand here in October and just one outlier here in July. If we decompose the data, we see the levels, the trend, and seasonality, also very clearly. So the first step is the step 5 is just define strength factors. So we have we take the sum of squares and divide by the sum of the sum of squares from seasonality with other factors for seasonality, and we do the same for trend. So those strength factors we range between 0 and 1. So for the example here, we have 0.96 and 0.80. So the seasonality again becomes stronger. Then we define the influence of seasonality and the influence of trend using the mean square. So we just divide the mean square of seasonality by the mean square of other factors, and the same for trend. And here, those are the F statistics in this ANOVA table. So we can set the numbers when we define there is no seasonal model. So if the seasonal, in this example, we have just 3, below 3, it would be no seasonal influence, and for trend the same. If it's below 3, we have no trend. So if both are below 3, we would select the non-trend, no seasonal model. So specifically here, we got 218 and 46 for seasonal and trend influence. So a very strong seasonality and also a considerable trend. So also we can transform these numbers of seasonality influence and trend influence into factors. So we would divide by 1 sum with the factor, and also the same for the trend. So those cutoffs would be defined empirically, and then we would have regions, a diagram of regions, determining each type of model to apply. So, for instance, with high seasonality and high trend, we could use a multiplicative Holt-Winters model, and for low seasonality and high trend, we could use a damped trend seasonality model. So this would be established for many lines of products so that we can automate the selection. in this case here, there's influence factors. So this is a kind of diagram. So as we use each time series to define the cutoffs here. It would be very time consuming if we apply it for each SKU, but we can apply this in an aggregate level and then use the aggregate level as a comparison for the bottom-up calculations. So this is a tool to use combining coming from bottom-up with top-down calculations for the demand. So with this empirical diagram, we'll have here in this region of low trend influence and low seasonal influence, so a model with no seasonality and trend. And here we have a whole to winters multiplicative, and here we have a dumped trend and seasonality. So for this example, we have also a table for the seasonality and the trend. And here's the results. So we got to the results that seasonality is high and also trend is high in this example. So we decided to apply whole to winters, and both with additive and multiplicative model. And also we decomposed the data in travel, in the level, slope, and seasonality. And this is the comparison of results. So this part here, before the red line, we have the history. And this here is the forecast for 1 year ahead. So we can see that the profile of seasonality is similar for both models. And if we zoom and look at the comparison of the models, we have a low trend here for additive, and then we compare to multiplicative. Multiplicative got a growing trend better than the additive method, but not super different results. So in automation, we would choose hot winters for this time series. So if we apply this many times, then we define this diagram, and then this can be embedded in automatic selection. So recapping, this is from data preparation, ANOVA, we define the factors, and then the empirical diagram. So this was a proposal for automated selection of model. And thank you for your attention. If you have any questions, so yeah.
Hey, thank you very much for your presentation. Then, yeah, let's open the floor for some questions. We have 5 minutes left. So are there any comments?
And also, if you want to get in touch with us, we also available on LinkedIn. So here's our contact. The data is available in this book, Changing Chains Embrace. And here is our LinkedIn accounts. We are very active there. Hans is always publishing posting about new essays that we test. So we would be very happy to meet you, everyone, on LinkedIn as well.
Okay, so if there are no questions, I maybe start with one. I'm not sure if I missed it in the beginning, but can you say maybe who is exactly the target crew for what you just presented? So who is this for?
This can be used in industry as well. So it's I use here an example for just a single time series, but in industry we would automate the selection of model. So many companies are not yet using APS. They don't have a program for the forecasts. Many of them are just using Excel still. So if the case, there's this step of selection of model, and this can be very time consuming, especially if you have lots of SKUs. So this would be applied in practice for aggregate levels, so that you can have automated model and calculation for aggregate levels, and then you decompose for the SKUs. So it's for industry.
Okay, and particularly for Excel applications as well, because there are some model selections in other forecasting support systems, right? So this is particular for Excel.
Yes, exactly.
Okay, thank you. Okay, any other questions maybe? If that is not the case, no?
I have one.
Yeah.
I have one.
Mm-hmm.
So I will put my camera on. Well, since you are focusing on ETS models, I was wondering whether you also compared the performance against the well-established performance of the ETS function in the ARP and the forecast package. So did you compare your solution against the benchmark baseline?
Well, after the selection is implemented, it is compared to, can be compared like for naives, but it's again, it's for when you have no program and you're working in Excel, or also just writing your code in R. So you have the models compared with naive, and then with each other, then decide if, this cutoff numbers for the influence factor and for the factors in as well for each line.
Okay, thank you.
Welcome.
Okay, and with that we are almost at the next presentation again. So 1 second, who is the last presenter for today, I think? Yes, the last presenter also. Jente, it's you. Okay, perfect. Then you can just go ahead.
All right.
Do you want me to give you the last 3 minutes to give you a sign?
Yes, you can do that. Thank you.
All right.
So now you should see my slides. All right, so hello everyone. My name is Jente, and I'm a PhD student at the VUB. And the work that I will present today is titled Valuing Lead Time in a Dynamic Order Up to Inventory System. And it is joint work with Ruben Krevits, who is a data scientist at OMP, and my promoters, Thias Guns and Professor Thias Guns and Professor Verbeke. So I will start by briefly sketching the context relevant to this work, and then I will continue with identifying the research problem and the research objective. So manufacturing companies devote a lot of resources to the planning of their supply chains. Gartner defines supply chain planning as the forward-looking process of coordinating assets to optimize the delivery of goods, services, and information from supplier to customer, balancing supply and forecasted demand. And in this work, we focus on supply chain planning at the operational short-term level, for which the goal of supply chain planning can be summarized as maximizing service levels while also minimizing production and inventory costs. In this regard, in this work, we focus on inventory management systems in which demand forecasts are critical inputs to the system. And so the figure on the slide depicts the information flow within a typical inventory management system for time varying stochastic demand. And so for a given inventory policy in each review period, demand forecasts together with system parameters form the inputs to a replenishment and inventory optimization model. And while the forecasts are typically updated each period, the system parameters are kept fixed in the short term. And so the optimization model then outputs a production, an order quantity, which can be a production or purchase order. And finally, this order quantity then may affect replenishment decisions in subsequent review periods, depending on the inventory policy in place. And so one obvious way to improve the inventory management system is to use improved demand forecasts. And one way to establish or to achieve this is to use so-called demand sensing techniques, which comprise forecasting techniques that not only use prior sales history, but also look at other or alternative demand signals, such as open sales orders. So, and this is exactly what we did in a previous study. So there we had data on open sales orders next to historical sales figures. And so the case study is based on data that was collected from the company Wallis, which is a Belgian manufacturer of poultry products. We had 3 years, or we have 3 years of daily data on 102 SKUs. And so, well, the main point of that study was that we were, as expected, using multivariate methods with the open sales order data resulted in better forecast accuracy for 1 to 5 step ahead demand forecasts. And so as expected, we achieved these results. While this is not the main point of this presentation, what we have to keep in mind from this study is that the gain in forecast accuracy decreases with an increase in forecast horizon, which again is as expected. Let us now go back to the inventory management system and find another way or a different approach to improve the performance of such a system. And well, if we look at another, or if we try another way, then we can consider changing the supply chain design. So keeping demand forecasting fixed, taking them as a given, and instead try to improve the system by modifying the design. the supply chain design, it affects how forecasts are being used and what forecasts are being used, and therefore changing the design allows us to align operational processes with forecasting capabilities. And in the case that he considered, inventory is managed via a periodic review dynamic order up to system, and demand forecasts are produced based on the demand sensing solution just described. And so in this specific context, we can then ask ourselves the following question: how can we modify the inventory system parameters in order to use the demand sensing solution to its maximum advantage? Sorry for that. Well, so in a dynamic order up to inventory system, the lead time is an important system parameter, and it directly determines what forecasts and what corresponding forecast horizons are needed as input to the system. Why is that? Well, because the lead time is the time between the moment when a decision is made about a quantity to produce and the moment when this amount is available to satisfy demand. And usually lead time is assumed to be given, either being deterministic or probabilistic. However, in many practical situations, lead time is in fact controllable. And in this work, we just consider lead time as a decision variable, while the inventory policy and the demand forecasts are considered as given. So to be more specific, the goal of this work is to develop a framework that can be used to identify for a given product for which inventory is managed via a dynamic order up to system. So to identify when or whether a change in lead time is beneficial compared to the current situation, compared to the current lead time. So in other words, we want to focus on aligning the controllable lead time with forecasting capabilities. Changing the lead time in an inventory system affects two things. So the first thing is the exposure to demand forecast uncertainty, and the second thing is the production cost. So with respect to the first, typically extending the lead time results in more exposure to demand forecast uncertainty, which results in higher safety stock levels and expected shortages for a given target service level, and therefore also higher inventory holding and back ordering costs. For the impact on production costs, we generally observe the opposite. So shortening the lead time results in extra costs due to expediting the production and or delivery process. And so changing the lead time thus translates into a trade-off between inventory holding and back ordering costs on the one hand and production costs on the other. Most previous studies on inventory management systems with controllable lead times focus on static inventory systems, which are suitable when demands are IID. And further, they also consider the cost of reducing the lead time to be the cost is explicitly characterized as a function of lead time. And so by combining these two elements, well, then we can determine the optimal lead time via optimization techniques. One exception to this is a paper of de Treville from 2014, in which they propose for the single period news vendor problem, a model to quantify the effect of reducing or extending the lead time on the exposure to forecast uncertainty in terms of a justified increase or required decrease in unit production costs. And well, in this work, we built on this model to develop a framework that can be used to make lead time decisions in a dynamic out system. So the output of our framework is similar, but the inventory systems considered are different. So both inventory systems are suitable when demand is stochastic and non-stationary, but they are different in that excess products and unfilled customer orders are not carried over from one period to the next in the single period news vendor problem, while they are carried over in our setting, so in the periodic review dynamic order up to inventory system. Well, this difference causes that the systems have different revenue streams and cost structures, and it also implies that they are affected differently by a change in lead time. So, well, and this carryover of excess products and unfilled customer orders implies that we have to take into account the uncertainty associated with the lead time, with the cumulative demand over the lead time in an order up to inventory system. So I will now give a high-level overview of our proposed framework, and to this end I will use a case study to directly illustrate how the framework can be used to determine what lead time to use. And so as our case study, we consider a specific SKU from the demand sensing study introduced in the beginning of this presentation. And so for this SKU, the inventory is managed via a dynamic out inventory system, and we have and the current lead time is equal to 4 days. And so we want to investigate whether it would be possible or it would be profitable to shorten the lead time so as to reap the benefits of the improvements in forecast accuracy. And so, however, for illustrative purposes, we consider candidate lead times between 0 and 5 days. Okay, but before we look at the proposed framework, well, we first need to understand how a periodic review dynamic out system works. So in this system, production quantities are set so to maintain a target service level, alpha, with minimum inventory and back orders. So that's the goal. And the optimal service level alpha, well, it can be obtained by dividing the unit back order cost B by the sum of the unit back order cost B and the unit holding cost H. And so in order to achieve this goal, at the end of each period T, well, first we update the inventory position by adding the items produced in that period to inventory. And next, demand is satisfied by either fulfilling it or back ordering it. In a second step, well, then the optimal optimal quantity to produce, or better, the quantity for which production should be finished in period T plus L, so T plus the lead time, is then determined based on the probabilistic forecast of demand over the lead time covering periods T plus 1 to T plus L, the target service level alpha, and the current inventory position consisting of inventory on hand and work in progress inventory. So to determine this optimal production quantity, we need a probabilistic forecast of the demand over the lead time, as it is the cumulative demand uncertainty over the lead time that causes inventory holding and back ordering costs. So the lead time does affect the number of periods that should be taken into account in estimating this forecast uncertainty, and also the associated forecast horizons. So it also affects the associated forecast horizons. Well, in this case study, to construct these probabilistic lead time demand forecasts, well, we first aggregate the daily 1 to 5 step ahead point forecasts to arrive at a point forecast of the demand over the lead time. And in a second step, we then move from a point forecast to a probabilistic forecast of the lead time demand by relying on historical out of sample lead time demand forecast errors to estimate this uncertainty over the lead time. And well, this approach allows us to capture both forecast errors or both that are forecast errors tend to increase for longer forecast horizons, and which is definitely the case in our case study, as we consider open sales order data next to historical sales. And second, it also allows us to take into account covariances between the forecast errors of the different time periods forming the cumulative demand over the lead time. So when for the case study considered, well, empirical densities of out of sample lead time demand forecasts, forecast errors are visualized here in the figure. And well, it immediately becomes clear that, of course, the cumulative forecast uncertainty decreases with shorter lead times. So now that we have the building blocks for our inventory system, we can look at the proposed framework. And as indicated earlier, I will only provide a high-level overview. Given that we are provided with a specification of demand forecast uncertainty for each candidate lead time and values for the inventory system parameters and the production costs for the current lead time, the framework then allows us to construct a so-called production cost indifference frontier. And to arrive at this frontier, we rely on the key principle that a company is indifferent towards lead times if the expected total costs are equal. And as production cost is a controllable part in the the controllable element in the total cost, well, the frontier summarizes the required or justified differences in unit production cost between the different candidate lead times to offset differences in profit due to changes in exposure to forecast uncertainty. So for our case study, well, there we use as inputs, we use the following inputs. So on the left, we have the demand forecast uncertainty estimations for each of the candidate lead times, as shown two slides ago. And to obtain the inventory system parameters, we start from a target service level of 90%. And this implies that back ordering 1 unit is 9 times more expensive than holding 1 unit of inventory for 1 day. And well, this also allows us to express B as a multiple of H. And finally, we also need a specification of the production cost of for current lead time, so C4. And since we express B as a multiple of H, we also need to do it for C4. And so to this end, management has estimated that the cost of holding 1 unit of inventory for 1 day is approximately 25% of the current production cost. So therefore, we can set C4 equal to 4. Well, and the resulting production cost indifference frontier for the example SKU is then visualized here on this slide. So on the x-axis, we have the different lead times, with the current lead time being 4 days. And on the y-axis, we have the corresponding justified or required percentage differences in unit production costs. And so, for example, shortening the lead time from 4 to 2 days, it implies that production can become 14% more expensive to keep the total cost unchanged. And for an extension of the lead time from 4 to 5 days, we see that the framework outputs that production should become 6% cheaper to keep the total cost unchanged. Now, of course, the question is, how can we use it to determine what lead time to use? Well, to that purpose, we need to combine the production cost indifference frontier with management estimates of achievable unit production cost decreases or increases. So that's how the model should be used for decision making. All right, so to conclude, well, in this work, we propose a framework that outputs a so-called production cost indifference frontier, which in combination with management estimates of achievable unit production cost increases and or decreases, can be used to support decision-making regarding lead time changes in periodic review, dynamic order up to inventory systems. The motivation of our work was to assess when and whether shortening the lead time allows us to benefit from improvements in forecast accuracy obtained by, for example, demand sensing solutions. And so finally, I would like to finish my talk with an interesting direction for future research related to this work. And well, that is to consider also uncertain supply next to uncertain demand. Well, an uncertain supply can be, for example, caused by quality problems, machine breakdowns, or transportation delays. So that was it. And thank you all for listening.
Great, thank you very much for the presentation. Do we have questions? Okay, so maybe while the rest is thinking about questions, I can start with the first one. I was just wondering, would that model also cover modularization of products? So what is it, how would that work? If you have modular products that split down the manufacturing process, can that be directly included, or would that be left to a decision maker in the end who uses that?
Well, that's a good question. I think so it should be possible, right? Because, well, here we are, we consider SKUs. So if they are a part of another product, that's possible. But the planning happens for a specific SKU, and so to effectively produce management estimates of these achievable differences in production cost, well, therefore you can use cost accounting systems. So we need management information to effectively use it for decision support, and it's on an SKU level. But as long as the modular product is managed as an SKU, well, we can apply it for that as well.
Okay, thanks. Okay, anyone else? No, okay. Then I would suggest with this last presentation, we end also the session for, probably not for today, but at least for the presenters now. And thank you. Thank you to the presenters. Thank you to all the listeners. And I hope you all enjoy the remaining conference and the remaining presentations.
Thank you, Marcel.
Thank you.
Thank you.